So in this video, I want to talk about chapter 13 in R and how to use R to kind of solve some problems from chapter 13 as far as the chi-squared test goes. And there's going to be basically two types of chi-squared tests that we're going to be able to solve here. The first is the goodness of fit test. And then the other is the association or the homogeneity test, which are going to be done similarly. So the goodness of fit test basically means that you have some data and then you have kind of a model for the data and you're trying to figure out whether or not it's a good model. So in this case, we have 4 values. We know the probability that each of these values is going to arise, and then we're trying to figure out whether the observed frequencies justify this distribution. And so just off the bat, it looks like no, because it looks like these first 3 values should appear with basically the same frequency. And the last value should appear a little bit more, which it does, but it doesn't look quite right. So we'll see if my intuition is right there, and we'll be able to quantify that. And so the way that we're going to do this is we're going to use the chi-square.test function. And again, remember the help function is there to give you all of the different arguments that you can put in there if you have a chi-squared test. And so here we're going to have, so here what we're going to do is we're going to have, let's see, our distribution. I just call it dist and make it straightforward there. I don't call it P because there's a P in the chi-squared test function. So we want to use the code P equals something. So I don't want to have P equals P in there. It just seems confusing and probably not good practice. So there's our distribution. Let's make sure that all the values add up to 1, just to make sure I ended them correctly. And then our observations, the values that we observed were 20, 21, 20, and 35. And so it looks like the total number of observations that we're going to make is 96. And then we want to see whether or not these 96 values fit that distribution that we were talking about. And so this is a chi-squared test. We're going to have our values that we observed, our distributions that we had. Our P is going to be the distribution, the probability there. And then with chapter 13, we always turn off the correction term. You always add in the correct equals false in 13, no matter what. So this correction term is what's called the Yates continuity correction. And basically what's happening is that if you think back to the binomial distribution and the normal distribution, how they kind of were comparable, they were kind of equal. So with the binomial distribution, as the number of rectangles increased, it looked more and more like a normal distribution. You can do kind of the same thing with chi-squared. There's a discrete probability distribution that you could compare it to. So kind of this correctness term, but we don't do any of that with MyMathLab. So anyways, the moral of the story here is that we turn off this correction term always. And then this is our test. So we have all this, and this is going to give us our chi-squared value, our P value, and then we can see how to interpret this from there. So we want to know basically the null hypothesis is that nothing happens, that everything is as it should be, nothing interesting happens, the data fits the model. So the distribution is the same as the given distribution, and that's going to be our null and alternative hypothesis for the goodness of fit test. Not too much to do there. The chi-squared value that we got from our R code was 9.875. And then our critical value, if you wanted to find the critical value, you again use the Q value. So we do Q squared. We have, let's see. So our critical value that we're looking at a 0.05 significance. Okay, so let's think about that. So our critical value 0.05, so that means that we want 0.95 to appear, there. And then let's see, we have 3 degrees of freedom. And so our critical value is going to be 7.815. So I had to think about that for a second. So 7.815. And we are going to reject because there's sufficient evidence. Notice that you reject because there's sufficient evidence. You do not reject because there's not sufficient evidence. And the other 2 answers are distractions. They're just never right. You can never reject because you don't have enough evidence. That doesn't make sense. You only reject the null hypothesis because you have enough evidence to overthrow what we already are assuming. So anyways, so D is the answer there. And that's really it for the chi-squared test, goodness of fit test. So I want to talk about numbers 10 and possibly number 12 if we need to. These are the tests for association and the tests for homogeneity. And so here we need to figure out what's the null hypothesis and what's the alternative hypothesis. And the null hypothesis is that is there an association or is there not an association? We just assume that there's not until we know otherwise. And then we can compute the test statistic. Now, to compute this test statistic, what we have to do is we have to actually enter our data as a matrix. And if we run a chi-squared test on a matrix or on a table, that's going to run the chi-squared test for association or homogeneity, which is a slightly different test than the goodness of fit test. So to store it as a matrix, what I'm going to do is I'm going to store the two rows here. So the diabetes and no diabetes, I'm going to store those. So we have 22, 21, 28, and 40. And then the no diabetes, just call it no, is going to be 199, 376, 287, and 201. And let me just add those values to make sure that we get 111. And for the other one, we should get 1063. And good, so that gives me a little bit more evidence that I entered them incorrectly. And then we're going to make a matrix, which I'm going to call M. And there's going to be 2 rows and there's going to be 4 columns. And our data that we're going to have here, our data is going to be the diabetes values and the non-diabetes values. And I always put in the values by row. So in other words, I put the values in a cross. And so if we put in our matrix M, this is going to give us 22, 21, 28, 40. So that's the first row. And then 199, 376, 287, 201. I'm not going to store it because I don't want you to see. I don't need to store it, but just to show you, if I turn the by row equals false off, that's going to input the data slightly differently. And so it's going to input the data 22, 21, 28, 40 according to the columns, not the rows. So you get 22, 21, 28, 40, and so on. And then the next data, and you put it in by columns. So anyways, that's what that code does. I always like to input the data by rows because as a mathematician, that's just how I think, is using row operations and doing things like that with matrices. So anyways, so that's our matrix M. So now what we're going to do is we're going to find our test statistic and we're going to run our chi-squared test on M. We're going to turn off the correction term and that's it. That's all we're going to do. And then our chi-squared test statistic is going to be 22.59. So we get 22.59. And our critical value, again, we can use the critical value. We're going to have, I always again have to think about this, but we have a 1% significance. So that means that we want the area up to that to be 0.99. We have 3 degrees of freedom. And then we want to round to 3 decimal places, I guess. So we're going to round that. So, so there we go. And that's going to give us 11.345. And that's our critical value. And then it turns out that our test statistic is greater, so we reject because we have sufficient evidence. Okay, and notice that the chi-squared test actually gave us a little bit more information than we needed. It also gave us the p-value. It said that the p-value is this value times 10 to the minus 5. So that's 0.0004917. Okay, so anyways, that's what that value is. So that p-value is very small. So that means that we reject because that value is less than 0.01. So that's that. And then question 12 is actually completely similar to this question 10. So I'm not going to talk about that. But the question 12 is basically saying, is there an association? Sorry, it's a homogeneity test. So yeah, so again, that's done completely the same way as question 10. So I don't feel the need to go over that either.